Alright, we come to the third applications of non-parametric tests by using Wilcoxon Rank Sum Test. Right now, this is a bit new to some of us, so I'm going to walk you through the guideline how to perform this test again. Right, so I'm going to pause here for a while. We're going to look at the videos on the guidelines on how to use Wilcoxon Rank Sum Test. Alright, so the procedure for Wilcoxon Rank Sum Test. Okay, let's take a look at this. The first step, okay, so before the first step, now usually we have to write down the objective of the research, which is the null hypothesis and the alternative hypothesis statements. Now thereafter we're going to rank all the uh, independent samples. Now, Wilcoxon rank sum test usually used to test on two independent samples. So one of the sample has a size m, the other sample has a size n here. Okay. Now most of the time, the sample m, size sample m is less than or equal to size sample n here. All right. So just to remember that. So maybe it's best if I write down at the side here. What I mean is now the sample size m usually is less than the sample size n here. Okay, right. Now once you have ranked that, okay, we're going to calculate the sum of the rank relevance to sample m, and then the sum of rank that is relevant to sample n. All right, and then thereafter, of course, checking. Don't forget to check whether the ranking has been done correctly. So the formula is still the same. We are still following the same arithmetics series formula. Okay, so that's given by half m plus n, m plus n plus 1 there. Right. Now, after checking through all this, we're going to analyze the test statistics as usual. Now, the test statistics T are determined by using the following rules. So if you are working on the lower tail test, therefore the test statistics will be the uh, sum of the rank for the smaller sample size m. If you're doing a upper tail test, so the test statistics is equal to these calculations here. So the m multiplied by m plus n plus 1, subtract off with w, where the w is the sum of rank for the sample m. And then as for the two-tail test, we'll have to compare between the w and the upper tails test statistics, and then decide which one is the smallest one. And then thereafter is the same thing. We're going to look through our data booklet on another set of table Wilcoxon rank sum test to determine the critical value. And then finally, to analyze the result, we're going to compare this critical value with the test statistics. So if the test statistics is less than the critical value, therefore we're going to reject the null hypothesis. Right? So I hope this procedure is clear for all of you. We're going to go back to the example now. All right, let's take a look at this example here. Okay, all right, let me move it over a bit. All right, Wilcoxon rank sum test is used to perform a test, a non-parametric test on two variables that are independent to each other, right? So example number 1 here. Now, in 2016, 9 economists made predictions for the growth rate in India, gross domestic product for 2017. Now, their predictions are shown below, together with 7 predictions for the growth rate in Chinese GDP made at the same time. So they actually predicted the growth rate, the GDP for both the India and China here. is there evidence that the economies are more optimistic about the Chinese growth rate than that of India? Okay, we're going to use this data and then test this at 5% significant level, whether there is evidence that the economies are more optimistic about the China growth rate than India. Right. Now, as usual, we're going to write down our null hypothesis and our alternative hypothesis. So here we can say that the um, uh, population's median population's predictions of the median, or we can say that the the population's median of population's median or population prediction of the median. Population median, okay, I think I write it down like this. Population's prediction of the median um, for for um, for both India and China is the same. Okay, so now that is the null hypothesis. Now, whereas for alternative hypothesis, we will say that the population prediction of the median predictions of the median for China is greater than India. Okay, and then there you have it, our objective. Okay, so once we're done with that, now what comes next will be very straightforward. Now, first of all, you can see that these are the predictions on the GDP growth between India and China, which is considered as the powerhouse of Asia in this case. Okay. And then the first step is to combine all these GDP between India and China. Okay, we make it into one list like this. And then once we are ready with that, okay, we're going to rank. We're going to rank all these lists as a whole. So this is the ranking that we have. Now, once we have done that, we are going to separate the ranking that represent China and India separately. So here I'm going to show you how we're going to separate the rank. So these are the ranking here. Yeah, you can see that this is India and China, and then this is your ranking, overall ranking. Okay, overall ranking. So you can see that 6.2. Okay, 6.2 actually belongs to India. So India has rank number 4 here. And then 7 belongs to India also, rank number 9. Whereby 7.2 rank 11. So 7.2 rank 11 here. And then there you have it. These are all the ranking between India and China here. Right? So I hope that is clear at this point. So all the ranking for both China and India, and then the list would go on until you finish up to rank 16 here. Okay, so I hope that is clear. So from here, once we have done this, what we need to do now is to actually calculate the sum of ranks that represent India. So sum of rank that represent India in this case, that will be all this. Okay, hold on. Okay, so that will be sum of rank for India, which are all this and this and this here. Okay, so let me try to calculate that. You have 25, 34, okay, 34, 40, 50, 55. So therefore, I'm going to write down the sum of rank for India. Sum of rank for India is 55. And then next, I'm going to calculate sum of rank for China now. So sum of rank for China will be 15 here. Okay, so 15, 25, 40. 40, so 40 will be 51. Okay, so 51, 51 and a 30 here, so 51 and a 30, 81. So therefore the sum of rank for China is 81 there. And then the sum of all this, so for checking the sum of this and China is actually 136 there. Right. Now by using the formula, we're going to use the formula to check here. So the formula we're going to use is um, half the total sample size for India and China here. So in this case, I'm going to write that down here. So now the smaller size usually is labeled as M. So the sample size for India is all right, sorry. The India is a larger sample size, so I used the wrong sample size here. So India usually is larger. So in this case, we use an N to represent. Now you can see that we have a sample size of 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 as a sample size that represent India, whereby M is a smaller sample size representing China here. That will be a 7 here. Okay, so we're going to take these two value and then substitute into the arithmetic series formula. Now that will be like 16 here, 17. All right, so that is 136, which actually tally. And then therefore we're going to check on this. We are almost there. Okay, at this point of time. All right, so I hope that is clear at this point. So next I'm going to simplify this, reduce this. Okay. Now what we need to do next will be to carry out the test statistics as usual. So test statistics. All right, so test statistics. What do we need for test statistics will be here. Okay, now the smaller sample size, so in this case we can see the smaller sample size is 7. So I will label the W that represent a smaller sample size as 81 here. All right, and then next we also need to calculate this value here, which is let me see, which is M plus N plus 1 here. So we need to calculate this value. All right, now that would actually give us let me see, that would be 7. 7 plus 9, 16. 16 plus okay, so maybe I just write it down here, 7 plus 9 plus a 1 here. Right, so there's actually 17. Okay, so 17, 119. So there's 119. Okay, all right. Okay, now once we're done with this, we're going to check what type of test that we are performing. So if you are performing upper tail test, so this is upper tail test. Now, since this is an upper tail test, we will have to take this value here, subtract off with W. Alright, so subtract off with W. Therefore, our test statistics, we will write it down as 119 minus 81 here. Right, so that will be 30. I assume that will be 38. Now our test statistics is 38 here. Right, so we have done most of the work now. Alright, so next we're going to refer back to our critical table here. Now the table that we are going to refer to now is very different from the first table that you have seen here. So instead we're going to look at the second table, the Wilcoxon Rank Sum Test. So here it gives you a lot of information about the sample size M and N, and then the formula that you're supposed to use. Okay, here I'm using the correct values here. The RM is the value W that represent the smaller sample size. Right? And then the table that we are supposed to use will be somewhere here. So maybe I just make it bigger a bit here. All right. Okay. So that will be the critical value for of W here. Now here we need to check our alpha is 5%. Our N is here, M is here, and then this is a one tail test. So I'm going to identify that one tail test. Now our sample M, our M is 7, so we look for 7. Our N is 9 there. Alright, so here I'm going to scroll up a bit. So sample size of 9, and then the M is 7. So M is 7. Let me make it smaller a bit. Do we have 7? Okay, still can't see the 7 there. Oh yeah, I think I know where is the 7. The 7 is right below here. Okay, so you can see that our sample N is 9. Okay, our sample N is 9, and then our sample M is 7 here. Sample M is 7, and then we are testing a one tail test at 5%. So at 5%, that will be a 5% pointing down. It leads us to 43 there. So here I'm going to um, simplify this. 43. Okay, 43. Therefore, from the data booklet, we found that the critical value is 43. And then knowing that the test statistics is less than the critical value, therefore we are going to reject. We have sufficient evidence to reject H0. Okay, by rejecting H0, therefore we can say that the population's predictions of the median, the prediction median, I just make it short here, for China is greater than India. All right. Or you can say that yes, there's evidence to suggest that economists are more optimistic about the Chinese GDP than India. All right. So I hope that is clear. This is how we perform our Wilcoxon Rank Sum Test. Okay. Now I'm going to move on to the second example shortly. All right. Let's take a look at our second example here. Okay. All right. In an experiment on cultural differences in interpreting facial expressions, 10 English children and 12 Japanese children were each shown 40 full-face photographs of American children who had been asked to display particular emotions in their facial expressions. Now, they were asked to describe the feelings of the children in the photographs, and the number of correct responses they made was noted. So the result is as shown below. Between English children and Japanese children here. Is there any evidence at 5% level of significance that English and Japanese children differ in their abilities to identify American facial expression. Okay, so now we're going to um, check this out in a while. All right, as usual, the first step is to um, write down the hypothesis statements here. So here I have already written down for this question here. Okay, the null hypothesis will be the median score for English and Japanese should be the same. It's the same. The alternative hypothesis would state that the median score for English and Japanese children is different. So this is a two-tailed test here. Right? So once we have done writing down the hypothesis statements, now we are ready to perform the ranking here. Okay. Now as usual, let me show you the original um, data is here. So all you need to do is write it down in one complete list, and then we're going to rank them as if this is the whole sets of data. Now once you have done that, we are going to split up all the ranking according to the one that represent English and then the one that represent Japanese. Take for instance, 16 actually belongs to English. Based on this ranking is ranking number 1. And then rank number 3 you can see that also belongs to English, and so on and so forth. Right? So once you've done that, the next step is to determine the sum of rank that represent English children, and then after that we're going to sum up the rank for representing Japanese children. So here I have already tabulated the sum. So the sum of rank that represent English children is 110 here. Okay, whereby the sum of rank that represent Japanese children is here 143. Okay, now bear in mind one common mistake that students usually did is if you write in such a configuration, most probably you may accidentally add up all this number. Bear in mind these are not the ranking. You are supposed to add up the ranking. So remind yourself on that. Okay. Now, once we have done that, of course, as usual, we are going to check whether we have performed the ranking correctly. Now, the sum of these two here, so the sum of the ranking, so WE plus WJ here, now that will give us 253 then. Okay, 253. Now I'm going to use that formula to check whether I'm getting the same sum of rank in total. So the formula will be half m plus n. So the sample size, I need to write it down here before we continue. So the sample size for the smaller sample, which is English children here, we have 2, 4, 6, 8, 10. So we have 10, whereby the sample size that represent Japanese children is 12 here. So for checking purpose, I'm going to key this one in, m plus n. So that will be 22 here, and then this is 23. So therefore, this is 11. So 23, 23. So 253. Yep. So it does tally. Right. Once we are happy with the checking sections, now we're going to move on to the test statistics. All right. I'm going to minimize this. We're going to go to the test statistics section. So for our test statistics, all right, for the test statistics, here we need to choose the smaller one between this. So the smaller one is actually W, which is 110. And now I also need to calculate these calculations here, which is m plus n plus 1 here, which is in this case a 10. I have 22, 23 here. That will be 230. Now between these two values, I need to choose the smaller one. So therefore my test statistics would be 110. I'm choosing the smaller one between this because I'm performing a two-tail test. So please refer back to the guideline on how to use Wilcoxon rank sum test here. So the test statistics will be here. And then next, I'm going to show you the MF19 one more time. Okay, now one of the drawback of using this data booklet is here. Now you will notice that the maximum sample size for M can only go up to 10, and then for N also the maximum is 10. But we notice that one of our sample size actually exceeding 10. Therefore, we can't actually use this table, but it does give us a suggestion how to go about this problem here. So for larger values of M and N, the normal distributions with mean and variance should be used as approximations to the distributions of W. Sorry, to the distribution of T in this case. Right. So we're going to use this here. Okay, I'm going to minimize that. We're going to calculate the mean and the variance for our approximations. So the mean is given by half multiplied by m. So m we have a 10 here, and then after that multiply by the sum of this plus a 1, which is actually 23 here. Okay, so that would actually be 115. Okay, and then our variance is calculated based on 1 over 24 m times n, and then multiply by 23 here. Okay, so 25 is 25, is it correct? Let me check. Multiply with this, and then multiply by mn23. So this is a 2, this is a 5 here. So 5, 10, 15. Right, so the variance should be this. Just let me check for a while. Alright, so after checking, I found my mistake. Okay, if you refer to the MF19 there, this value is supposed to be 12. I keep on remembering as 24, so it's 12 here. So if this is 12, now I need to multiply by 2 then, so that will be 230 then. Alright, now we are good. Right? So having this, we are trying to, because this is a two-tail test, right? So two-tail test, okay, and then our lower value is this. Therefore, I'm trying to evaluate this probability here. Okay, even though it's two-tail test, but because t is the smaller between this, so therefore I'm actually trying to evaluate this type 1 error, which is the alpha itself, the test statistics value here. So that is 110. But because 110 is a discrete, we are trying to use continuous distributions to approximate the discrete variable. Therefore, we have to make a bit of perform a bit of continuity correction. Therefore, this one we can write it down as, I put a star here, meaning that we have actually done the continuity corrections, which is actually 110.5. So you have to plus a 5 there, and then convert that to z-score. So convert that to z-score, that will be 110.5. Subtract off with 115, and then divided by 230 square root here. Okay, and then I'm going to use my GeoGebra to evaluate this faster in this case. Okay, so we have a normal distributions. The mean is this, but the standard deviation is square root of 230. Okay, and then I'm interested to evaluate the left hand tail, which is this, and then based on my calculator, it is shown that this probability, if you refer to the data booklet, you will also get the same number here. All right, so just for ease of calculations, so I just write it down here. So that is 0 0.0, oops, 0 0.0, 0 0.38, uh, 3833 there, right? 0 0.3833. Okay, so I'm going to write it down. 3833. Right. Now that will be the probability, and then because the all right, now I'm going to simplify this. Because the alpha is 5%. Okay, because the alpha is 5%, and then this percentage here is actually less than 5% here. It's actually less than 5%. So I'm going to write that down here. You can actually draw out the normal distributions here. So maybe I'm going to roughly draw it here. So you can all right, so I'm going to draw the curve there just to verify the result that we are getting. So right here we have a normal distribution curve, okay, and then we have our test statistics value here. That is around 38%. So 38% is quite huge here. So this whole thing is 38%. Whereby our significant level, our rejection zone is only 5% here. So it is quite obvious that our test statistics value that is located outside of the rejection region. Therefore, we are going to, oh sorry, we fail to reject our null hypothesis, or in general we say that, maybe I make a remark first. So we know that this is much greater than the 5%. So therefore, we're going to accept the null hypothesis. So accepting the null hypothesis basically conclude that the median score for English and Japanese is the same. So there's no difference between the median score between English and Japanese children, right? So I hope that is clear. I will move on to the last example shortly. Right, we're going to look at our last example on how to use Wilcoxon rank sum test. Right now, the question state that determine 1% one tail test or 2% two tail test in this case. Right, 1% one tail or 2% two tail. Yeah, correct. Critical value for the samples with size M 33 and N equal to 58 there. All right. So how are we going to do that? Now, first of all, because the size already exceeds 10 there, so therefore we have to use a normal approximation in this case. Now, our normal approximations will be, we're going to determine the mean and variance itself. So let's try to determine the mean. So the mean is calculated as half m. So the m is 33 multiplied by 33 plus 58 plus 1 here. All right. And then therefore that will yield, let me see here, what do we have? 34, so that would be like 92 here. So 92, that would be like 46. Okay, 46 by this. Let me see if I can do the math very quickly here. That is 46 by 11 here. Sorry, yeah, by 11 here. 46, 46. And then that will be a 506 there by a 3 there, so it will be 18. Now that will be 1518 there, right? Now of course I need to check that out using my calculator. Sometime I might make mistake when I'm recording, especially. Right. So let me give that a try. So that will be like 92 okay, by 33 there. So 1518, right? Exactly the same. Okay, I'm happy with this. And then next I'm going to calculate the variance, which is 1 over, oops, I keep on writing 1 over 24. So it's supposed to be 1 over 12. Okay, just to be careful on this. So 1 over 12, let me correct that. Okay, alright, so 1 over 12 multiply with mn, so 33 multiplied by 58, and then multiply by this. Okay, now that would be a very huge number to work with here. Let me see here for the 6 here by, oops, it's not for the 6 there. Let me see here. Okay. Um, right. So I'm actually getting like 14674 there. Alright. So just let me check one more time if I got this correct. Okay. Divide by 12 there. Alright. So 14674. Right. So that will be my variance here. Right. Okay, so at this point of time, I'm interested to find out the critical value. So from the previous example, we know that by choosing the smaller t value, I'm actually interested to find out this critical value t here. And then don't forget t is a discrete number, so therefore I need to perform a continuity correction here by adding a 0.5 here, and then this would be, okay, so I'm going to write down the formula first. This would be t plus 0.5 subtract off with 1518, and then divided by the square root of 6 here. Alright, now okay, now because we are doing a one tail test or 2% two tail test, so 1%, meaning that this probability here, this one here, should be less than 0.01 here. Okay, so this whole thing should be less than 0.01. Okay, so now let's look at what we have here. Oh, oops, sorry, I think I made a mistake here. Now, after the continuity correction, yes, we need to increase it by 0.5. But at this point, I think I accidentally convert that to z-score, so I shouldn't be using t star anymore because this one is the z-score. Right, so luckily I noticed that. Now, once we have done that, all we need to do is you can refer back to your data booklet there. Data booklet one more time. It's just that the only difference now is we are looking back to normal distribution. So I'm going to go back to a normal distribution here. So where is that? Okay, normal distribution, less than 0.01%. Okay, less than 0.01%. Now, because of the shading of the configuration of this data booklet here, now I'm actually looking at the 99%. So I'm supposed to look for any region here that says 99. 99%. Okay, 99% should be somewhere here. Okay, you can see that that will be somewhere here. That is 2.3. 2.32, and then you can choose here if you want to be more accurate here. So 1 2 3 4 5. I think we have 6. I think there's 6. Let me correct that. Or 1 2 3 4 5 6. Okay, so that's actually a 6. So we're looking at 2.326. 2.326. Right, 2.326, which means this is actually anything less than negative 2.326. because it's a left hand tail. So less than 236. Okay, anything less than that, therefore we can actually write down this as t plus 0.5 minus 1518 divided by 14674 here. That would be anything less than, this value will be anything less than 2.326. Okay, and then from here we're going to solve it manually. So I'm going to solve it manually here. It's kind of tedious. You can see that 14674. Is that 14674? Yes, correct. Okay, so I need to multiply that by 326, 2.326, 2.326. Yes, correct. So that's what it is. And then after that, I need to add up with 1518. Okay, and then after that I need to subtract off with 0.5. 0.5, yep, correct. So therefore I would be able to get a t less than 1799. Okay, is that 1799? Oops, I think I made a careless mistake here. Hold on, just let me try out again. Okay, just let me clear and try one more time. I think I made a mistake here. 14674. Okay, by 2.326. 2.326, yes, correct. Okay, so therefore I need to actually 1518. Okay, correct. Now this is this, and then this is positive, so I need to add a with 0.5 here. So therefore the t value, the correct t value would be here. I'm going to write it down now. 1235.7. Right. So from here we can conclude the critical value. The critical value is 1235 then. So anything less than 1235 will be considered as the critical value. All right. So I hope that that is clear at this point. Alright, so thank you very much for watching. If you like the video, don't forget to subscribe and then click on the notification bell to receive the latest videos on any mathematical topics.